Okay, students, hello again. I hope you're all well and ready to hear something about the data analysis again. So today we have at least a couple of topics. Can you just think something that you can hear me well? As well, I will try to share the whiteboard. Yes, so it's okay. Start sharing. Okay, so I'm sharing my whiteboard. So today we have to cover at least two topics, which I want to do. And the third one, I don't know if we will have some time. We'll see. But as you might recall, a week ago, we have started looking into the classification problems. And what we did, we actually have formulated the problem of linear classifier. We have drawn this into the infinite space, the linear separation of two classes in the binary classification problem. As well, we have played around and have shown you some intro into the probabilities, and then have turned into the logistic function, which basically is used heavily in classification and specifically in the logistic regression. So basically today we will have to get deeper into the logistic regression. So I hope it works. Let me see. This guy whiteboard doesn't work somehow. Come on. Okay, guys, something's wrong with my whiteboard. I will try to reconnect it. Okay, let's see. Okay, now it's okay. Sharing. Your whiteboard. That's okay. Now it seems to be fine. It was a glitch. Okay, so I hope you can see it now. So we will go through the logistic regression. This is the first topic. So basically, logistic regression. Even though it has a name regression, but since this is logistic, it basically maps linear output, the score, into the probability space. So that's why it is a method for classification, not for the regression. Okay, so in order to express the actual cost of classification, we need to formulate as a function which need to include a probability. So basically, for expression of the overall cost for the classification for all the probabilities in combination, we are using not summation like we did in the regression tasks, where we wanted to minimize or sometimes maximize output. We basically were trying to minimize residual sum of squares. But here we want to actually maximize the probabilities, right? So in order to combine probabilities into one piece, into one function, what is actually being used, it is a product, not the sum. So basically, it is coming from the fact that probability, independent probability of A and B is actually equals, so two independent events that happen together, that A and B would happen together, equals to the probability of A multiplied by the probability of B, right? So this is a product, as you can see, not a sum of the probabilities. So for instance, if we have six-sided dice, right? Six-sided dice, so the probability that we roll one, right? So for instance, probability of rolling one equals to 1/6, right? Because this is one of the sides. So once we roll a dice, the probability that we get a certain number is actually 1 divided by the overall possibilities, right? So we have 6 possibilities for the dice to get a number. So probability of 1 is actually 1 divided by 6. So the probability of rolling 1 and then again 1, right? Again 1 is equal 1/6 times 1/6, right? So basically we need to multiply these two guys. So probability of these two events happening one after the other, or two independent events happening together, is actually 1 divided by 36 now. So it's much less likely than it would be the single event, right? So exactly the same thing we have to do with the probabilities of for all the data set, right? So with all the data set, we have to take the product I equals 1 until n for all the events, right? This is the product multiplication of probabilities, right? Probabilities yi being in yi given xi and w, right? So this is a product of all probabilities, and our task will be to maximize this, right? To maximize with respect to w. So we want to maximize this product of all probabilities for all our data set. So once we find a solution for this equation, then we can tell that we have found some optimal value, right? So basically, this is what we will be looking at mostly. So this kind of equation is being called the likelihood function. Likelihood function. Okay, so this is likelihood function, and it is lower letter L. This is how we will write it down. Okay, so likelihood function is actually the product of all the observations in our data set, probabilities of them being in the right class, given the input vector and VW, right? Weights that we are about to find and optimize upon. Okay, so now I will give you a couple of expressions which are basically very frequently used in this type of. We have probabilities and we want to express something into the probabilities. So basically, since our problem is a binary problem, and we have a class expressed in the space from 0 to 1, right? This is a binary problem. I'm stressing this. This is a binary problem, right? Problem. Okay, this is a binary problem, what we are doing. So basically, likelihood function can be rewritten in a form that we would use not a different class for all the events. So basically, this we expect 0 or 1, right? But we can rewrite it to be expressed in a single probability for the single class, for instance, for 1, right? So let's rewrite it a little bit. So basically, a product I equals 1 until n, given that yi equals 1. So basically, given that class is 1, equals to the product of probabilities, 1 being 1, given xi and w, right? So we express not a variable class, not like a variable, but as a constant of being in class 1, right? So, okay. And we can multiply this by the probability, by the product of probabilities, I equals n, with the condition that yi equals 0, right? So the different class in the binary classification problem. And this is actually 1 minus the same probability, xi w. Right, so what we did, we actually have expressed not the variable class in our equation, but have expressed through the same class probabilities being in a first class or in the second class. So we just don't care. We have exactly the same term here, exactly the same term here. So since we have the binary problem, we can do this. This is not a problem, right, for us. Okay, because we have a rule that P being in 1, right, given xi, right, and w, plus being in 0, if you can remember, xi w equals to 1, right? Because this is all either 1 or 0. There are no other options to express this. So we can take this 1 into the side, and this can be expressed like that. Okay. So now we will play around, and what we will do, we will try to derive this and to find the gradient, right? So basically, again, we need to derive that guy. Okay. So in order to derive this product equation, we actually have to do a trick. So here I'm just drawing a line to myself, and on this side I will write various rules that will be used on a way. So one of the rule is basically named that that's being used right away. It is called the logarithm of products. So basically we will use a rule that logarithm of a times b of product of two variables equals logarithm a plus, this is too far away, let me scroll like this, logarithm a plus logarithm b. And another rule is that logarithm of a divided b equals logarithm a minus logarithm b. Okay, let me fix that a little bit. So here I will write various rules. Come on. Okay. Okay, here I will write various rules that are going to be used on the way. Okay, so having made that, we want just to get rid out of these products, because products are not very nice in order trying to get the gradients, right? To trying to derive the equations. So we will use these things in order to get rid of the products. So basically, in order to get rid out of the product, we basically will take this likelihood, right, and we express it in the logarithmic notation. So basically, log likelihood, this is log likelihood, log likelihood function, just has exactly the same properties like we had before. So log likelihood function, right, w equals just a natural logarithm. I will write it as log, not ln, but log, logarithm of the likelihood function. So basically it has the same properties. If we want to maximize it, maximize. If we want to minimize it, minimizes. No problems about this. So, but we basically put this under the log in order to get rid of it by using, get rid of a product in order to use this rule, right? So we can use now this rule and to get out of these products which are standing in our way, actually. So now we can express this. Okay, let's continue. This is log likelihood. We can express this as a sum, right? As a sum, I equals 1 until n. So now we have got rid out of these products, and now we take yi, right? Yi, and now we still have our log hanging around. Log p y equals 1, right? So 1 given xi w plus, so now we are in the summation, we do not have any products anymore, right? Plus 1 minus yi, and again log, and 1 minus probability in being 1 given xi w. Okay, so basically we have expressed this as the sum. So what we have now, so this part of the term, right? If yi, the actual class, right, equals 1, then you just multiply by 1, then log, and that's it. So basically log of p being in 1, right? Else, then yi equals 0, the actual class is 0, right? Then this term becomes 0, right? So basically we make sure that this term only is evaluated when the actual class is 1. And this term is vice versa, right? If yi equals 1, then we have 1 minus 1 is 0, so it is 0, right? Else equals log p1. Sorry, log, oh, it started working. Log 1 minus p1. Okay, so basically it's p0, right? So this way we make sure that the current existing the actual class determines which part of this equation is actually being evaluated. Okay. Now we make some additional notations in order to simplify the upcoming calculations. I have already mentioned you, and you have seen that sigma of A is actually equals to sigmoid function 1 plus E minus A, right? So this one we've seen already, but I'm just writing it down so you know what sigma is. And let's make up for us an alpha I term variable. So it will be a sigma, and we will put W transpose H xi, right? So this basically for ifs observation y hat, right? So this is a probability of ifs observation. Okay, so after doing so, now we can slightly simplify the actual these two functions, likelihood and log likelihood functions. So let me try to do this right away. So okay, so basically likelihood function can be simplified in this way, that we had a product I equals 1 until n. Okay, this is an old notation, but anyway, yi xi, just repeating it, w And now in the new notation, right, this is the product again, I equals 1 until n, the product. So basically we take alpha I, right? So basically the probability of being I, right, times yi, right, times yi, and multiplied by 1 minus alpha I times 1 minus yi. These are various different expressions of the same thing, but just for you to understand that this can be expressed in various ways. And in literature, you might see them, but they are basically talking about the same thing, that this part, if yi equals 1, then we get 1, so we get alpha I, else we get 1, right? Okay, so this is basically a product of different objects that tend to be in the right or not the right class, and we basically try to make this product diversify by the current class, by the actual class. So this, in contrary, if yi equals 1, then 1 minus 1, right? So this is 0, it becomes 1, else 1 minus alpha I. Right, so we have just expressed in a slightly different way. So you have it expressed and you can recognize it. Okay, so now log likelihood. So we move to the log likelihood. Log likelihood is a good thing because it doesn't have this this nasty product term, right? So we have again the sum plus 1 until n. Okay, so we have again yi, and this is log alpha I, all right, plus this is sum 1 plus 1 minus 1 minus yi, the actual class, and log 1 minus alpha I. Okay, so this is again the same rule, right? The same rule. Because this one is 0 or 1. If yi equals 1, then log alpha I. Else 0, right? 0. This side, if yi equals 1, then 0, else log minus 1 minus alpha I. Okay, so I guess you understand this. These are just the different expressions, different way of writing down this likelihood function, which we have put here as the product of all the probabilities from the data set, right? From 1 to n, we move all the observations, we multiply these probabilities. So this is not very handy for the derivatives, for calculating the gradient. So what we did, we have basically applied, we have split into the same expression for the probabilities of 1, right? Being in 1, 1 minus 1, right? And what we did, we applied the logarithm multiplication rule, right? So we basically we now have the log likelihood function, which is expressed in a good way. So we can work with this and we can find the gradient. Okay, so moving up. Okay, so now we have two things. These things, yi and 1 minus yi, is actually the identity. identity terms. These terms just tell that we should take that part of the equation. So these guys are not the subject of the derivatives. They are special things. Special, right? Special. So we basically don't care about these things for now, right? So let's take care of the log alpha I and log 1 minus alpha I. Okay, so moving forward. So basically, let's take the first thing, right? Which is log alpha I, right? So logarithm of being in class 1, right? Being in class 1. Okay, so what we basically can do, we can take this log alpha I, which is equal to log, right? To log 1 divided by 1 plus E minus W transpose H. So basically, I just took this guy, which we had just here, right, and have expanded it back, right? So it's not simple anymore. But now, since we have a logarithm of quotient, right? So this is a division, logarithm of division. What we can do, and we can simplify it, right? So we can apply this rule, right? So A divided by B, logarithm of A divided by B, we can do logarithm A minus logarithm B, right? So basically this is a logarithm of 1 minus logarithm of 1 plus E WTH, right? So basically logarithm of 1 equals 0, right? Equals 0. So our final expression here is this one, right? So this one goes away. So we have this expression left, right? For us, it's simpler. It's simpler than that we had before. So basically now we can try to find the derivative of this guy. Right, so the derivative with respect to Wj, to one of the parameters, to one of the dimensions of log alpha I, right, equals to, okay, now a couple of rules. A couple of rules I need to add here for your convenience. So the derivative of logarithm of x, right, is equal 1 divided by x, and the derivative of x, right, derivative of x. Okay, and the derivative of ex, so basically the derivative of ex equals ex and the derivative of x times the derivative of x. So having these two rules, we can move up. So 1 divided by whatever was under the logarithm, right? So this basically gives us, so we are deriving from this function, right? This function. So this is minus 1 divided by the 1 plus E minus WTH, right? So we have this part, right? This part here, and now we have to express the derivative of x, right? So the derivative of x, let me write it down. Derivative of Wj, partial derivative of this guy, and this is a function 1 plus E minus WTH. Okay, so we can move forward. So derivative of this guy, so basically one goes away, we have to repeat this ex, right, and then the derivative of this guy. So basically we just have a minus, so this guy need to be repeated, right, e minus wth minus wth, and on the denominator 1 plus e minus wth, right? So basically repeating the same thing, right? So we have expressed that guy by this rule, okay? And now we have to derive this remaining part, right? This remaining part, and this is actually, as we already did this, right? Let me repeat it again anyways, so you will have all the steps, wj, and this is minus wth, right? So we did this before, and this is xi actually. I'm just simplifying. So basically we did this before, so the derivative of this guy is actually the jth feature, because we are deriving for the jth term, right? Jth term. So this is jth feature, right? And this, since this is minus, we're just adding in minus. So we have minus, minus, right? So then jth feature, right? Jth feature. And now e minus wth, right? And 1 plus e minus wth. Okay, so these minuses turn to plus, all right? And now we can rewrite this slightly into the h, into the feature, h feature, times something. And what it is times, let me write you some additional rule. So since we had this, I have it, let me put some light. Okay, since we have this, since we already had this rule, so basically being in class 1, right, in class, okay, let me put in class 0, being in class, probability of being in class 0, right, with having given xi and w equals, as you already know, 1 minus being in class 1 in a binary classification problem, right? So this rule implies that this actually equals to 1 minus and the sigmoid function, right? 1 plus e minus wth, right? So we basically can simplify that. So we will have 1 plus e and all of this, right? So 1 plus e and 1 plus e here. So we basically simplify this by, okay, let me try to write this 1 plus e minus wth, 1 plus e minus wth, right? And this is minus 1, right? So all of this equals 2, these 2 goes away, right? All of this equals e minus wth divided by 1 plus e minus wth. So this is actually the probability of 1 minus the probability of being in first, right? So this is the expression. This is the expression we were looking for. And now look at this. We just got that expression here, right? We just got that expression here. So this is nothing else like 1 minus alpha I, right? Because we had alpha I as being here, right? This guy alpha I. So basically by looking into that rule, we just express as 1 minus alpha I, this term. Okay, so we have found the derivative of natural logarithm of a alpha I. So natural logarithm, this part, this the first part, let me write down here the first part, right? The first part, the derivative of this part is actually this term. So basically feature, j feature times 1 minus alpha I. And this is how this part changes, right? At a given point. And here is the second term. The second term we will be deriving right now. Okay, so let's do some simplification again. So this is the second term, and it looks like log 1 minus alpha I. Okay, so basically this can be simplified as well, as you can expect, 1 minus alpha I, right? So basically by looking into this guy and into that rule, you can see that we can express 1 minus alpha I as this expression, right? As this expression. And so basically this becomes a log, right? E minus WTH and 1 plus E minus WTH, right? So again, this is logarithm, division, right? So we can do the same trick with the subtraction, right? So this becomes a log E minus WTH, right? And minus the upper part, right? We don't denominate log 1 plus E minus WTH. Okay? So now what we have here, since this is a natural logarithm, again, I'm writing this is natural logarithm, right? Natural logarithm. So we have a rule, right? So the log of E x equals x, right? This is by the rule of logarithm. Okay, so now we can rewrite this as being a minus WTH, right? Minus WTH, and this one is just minus log 1 plus E minus WTH. Okay. Okay, so this one is the expression that we can attack, right, with the derivatives. So let's take a look what we have here. Okay, so the derivative of partial derivative with respect to one of the weights, right, of log 1 minus alpha I, right, is equal. So derivative of this guy, the first term, is actually the feature, right? The j feature again. So h j feature, right? We go to the j feature. And this guy, this is a logarithm. So again, minus, we need to put it 1 minus this term, 1 plus E minus WTH, right? So this guy. And now we need, okay, let me repeat it again, the derivative of WH. And now we just need to derive this guy, what's left. So this is 1 plus E minus WTH. Okay, so basically the same trick again. It equals to minus feature, sorry. Okay, now minus. So again, we have the same thing that we had before, right? Just the same thing that we had before here. We just had the same thing. So it basically takes this term up, right? This term up and multiplied by the feature. Multiplied by the feature, nothing else, right? So we can go there right away. Right, so this becomes minus HJX I, right? So this is feature, and E minus WTH. Okay, and the denominator is 1 plus E minus WTH. Okay, so now we can simplify this a little bit. So we have something like this with feature, right? So minus feature, HJXI, right? Minus minus, so it becomes plus, right? It becomes plus. Feature, HJXI, right? Feature, and again, here is the same guy, right? 1 minus alpha, right? 1 minus alpha I. Okay, so good. Now, if we would spread this out, so basically minus feature plus feature, right? Minus feature times alpha, right? So these two terms go away after this multiplication expression. Okay, let me write it down anyway. HJXI, this is plus HJXI, right, and minus HJXI alpha I. So these two guys go away. So what we get, finally, we get minus feature alpha I. Okay, so this is the second part. This was the second part. Oops, the first part and the second part, right? So this is the second part, expression for the second part. Okay, so now let's plug it in. Let's plug it in. So I basically write it all, okay. No, all is not good. Let's make it something different. Come on. Okay. So let's make a star. Let's make a star. So star basically means that we will combine everything, right? So combine 1 and 2. Okay, so our final derivative of weight j, one of the weights, right, in a function of a log likelihood with for the given weights, right, for the given weights equals to sum of all our values, right, all values. And now we have the identity function. So we have an identifier, identity function, right? And now we take this guy from here, feature times 1 minus alpha I, right? So now we take feature jth feature, right? Jth feature xi 1 minus alpha I. Okay, feature and plus identity function for the 0th class 1 minus alpha yi. Right, identity function for the other class, and here we just put this term minus feature xi alpha I. Okay, so we just have got the full function. Now we can simplify it a little bit, right? So we need to spread it out. 1n. So this is a sum. So let's divide this guy inside, right? So hj xi, right? So times 1 minus yi hj xi alpha I. All right, so I basically divided it out. And now we can multiply these guys together, right? So spread it out. So 1 becomes minus hj xi alpha I. All right, so this guy and this minus minus, so it becomes plus hj xi alpha I yi, right? Okay, so can we remove something? And yes, apparently we can remove that guy, this is minus, and that guy, this is plus, right? So again, this becomes equal to y1, and so our derivative, our gradient for logistic regression becomes, okay, so these two guys are the same, so we can basically take out the feature, right? Take out the feature, so hj xi, right? We're taking out the feature, and this is yi minus alpha I. Yep, that's it. So this is the gradient, logistic regression gradient. Now, if you would take a look into this, this is exactly the same what we had for the perceptron, actually, right? Remember, for perceptron, we had a minus between the classes if we are not correct or not correct. If we were correct, it became 0, so we did not have any changes to make. Otherwise, we just have multiplied with a feature, right, or the column. So this is exactly the same. So you see, we have made so many calculations, so many derivatives, etc., right? The long whiteboard, but we have come up to the same solution, right? And this is incredible, right? The same solution actually can be found from such a long way. Okay, so now the logistic regression algorithm, one of the options could be like this, right? So now we need, since we need to maximize, this would be the gradient ascent. Okay, gradient ascent algorithm for logistic regression. Okay, so in it, initialize the weight with zeros or random, right? No, then the feature vector is actually equals to the feature vector, yes. So you can pre-calculate that guy beforehand, right? Okay, now let's put some kind of the guy for the vector of predictions. So let's put A. So these are the predictions. Predictions in probabilities, right? So these are predictions in probabilities, not 1 and 0, but the probabilities. So we do exactly the thing we did so far. So this is basically the sigmoid function, 1 divided by 1 plus E minus WTH, right? Oh. So basically we calculate the probabilities. So these are our predictions. And now the gradient equals to vector of actual classes minus predictions, right? Just like we had here, right? And we have this vector, then we can do the transpose, right? We can do this transpose and multiply by the feature vector. Feature matrix, actually, this is feature matrix, right? Since we have all the features here, so we don't loop. So this is totally vectorized solution where we have matrices and vectors only, right? So this becomes a feature matrix. Okay, so this is the initial calculation. Then we have weight 0. So now we can loop while the gradient transpose times gradient. These are gradient vectors for each of the weights, right? These are gradients of each weights. So basically transpose. So these are basically squared gradients squared, sum of squared gradients. Sum of squared gradients, or we can express this. This is equal to the second norm of gradient, right? Second norm of length. So this is basically length vector for all the gradients. So what we have here, if it is more than epsilon, right, hyperparameter, if it is still more than epsilon, so we haven't reached yet. So what we do, we calculate new weights. So weight equals weight plus eta, so this learning rate J, right? So basically do the same thing. We want to maximize, so we plus it up. And now we recalculate the probabilities, right? The predictions, 1 plus E minus WTH, right? So basically recalculate the probabilities, we make predictions, and now update, and now look into the gradient. What the gradient do we have now? Transpose H. And this is a gradient ascent algorithm, which basically tries to maximize the logarithm of probabilities, right? Of all the probabilities, sum of probabilities. Okay, oops. So, okay, let me keep up. So these are initial calculations, and then while loop until we meet the condition. So this guy is the hyperparameter alert. This guy is again hyperparameter alert. Okay, and we just do these calculations, right? So the difference with respect to the perceptron, actually not that much. The biggest difference is that we actually do this guy, right? We calculate probabilities, but the gradient calculation term is more or less the same like we had, even though we have made so many calculations in order to derive the gradient, but actually the results the same. Okay, so this is one of the topics I wanted you to show. This is the logistic regression gradient descent algorithm. If you have any questions, please type in or tell something, because now I will be going to a different topic which I want to give you today. Okay. So since I don't have any questions, everybody seems to be excited. That's good. So now we will go into something which is simpler, I would say, in some sense, right? And more, and the thing that you might be more familiar as a programmer. Will we have it to use for a lab class? That's the question from Victoria. It depends. It's up to you, because you have to do it by yourself algorithm, so you can choose what you would like to implement. You can take the simplest one, the perceptron, for instance. You can take the decision tree algorithm if you want, or you can do this. This is not that difficult, I would say. The derivation is difficult. You might think, I don't know how much familiar you are with maths, but the implementation is not that difficult. So for your implementation of classification algorithm, it's up to you. You choose. Okay. You are not required to take this one. You can take any of what was taught at the class. So basically now for reclassification, I've showed you an algorithm of perceptron. I mentioned a little bit Adeline and showed you the algorithm of gradient descent for the logistic regression. Now we will move into a different kind of an algorithm. This is a decision tree. Decision tree classification. Okay, so the decision tree classification is basically a so-called greedy algorithm, which in essence, what it does, it basically takes simple decisions and tries to find the global solution, global optimal solution, by taking a very simple decisions. So basically, what I will present you right now is basically the algorithm itself, and then we will go through the example, so you will understand how it works. So this is another option which you can implement in your homeworks. Okay, so decision tree. This is the master function. Let's say so. It has X and Y, right? So decision tree construction basically starts from the input matrix and the actual classes, right? The actual classes, as you already know, right? So basically the meta algorithm looks like this. If not stop condition, then what we do then, if we have not met the stop condition, we will go through each of the steps. Right now I'm giving just to you a meta algorithm, the top level. So now we find feature to split. All right, find the feature to split. Basically we pass X and Y again. So this is again some kind of a function which we need to elaborate upon, right? So stop condition we will talk about, find feature to split we will talk about, okay? So now for each split, right? For each split, so we actually have split on some feature, right? So for each split we've just made, right? What we do, we just call recursively the same algorithm. Decision tree, so X split and Y split, right? These are two partitions that we have already split our data upon. We will look into the example, no problems about this, but I'm just basically giving you the top level algorithm. Okay, so now we need to find out what does it mean to find feature to split. All right, so let's talk it over. So basically find feature to split, all right, find feature to split. Okay, and it was given an X and Y. Okay, this is either the whole data set or a partition, right? So what we do first, we just initialize the variable which we call the impurity best, and we assign it to +infinity. So basically impurity so far is the +infinity, the biggest possible, right? And let's store for us split best, right? And the best split is actually 0, 0. Okay, so now we go through each feature, all right? For I in 1 until P, right? In X, all right? So basically we go through each feature, right? So here is basically loop each feature, right? We are looping each feature, right? So basically looking into this. And now we just basically try to split it, right? For each j in splits. So basically there are some kind of a condition where we can split, right? So we will talk it over as well. So for each split in xi, right? For each split in this feature vector, right? So we will talk this over. I'm just underlining. For each split, what we do, we calculate the impurity. Impurity equals some kind of a function I with wj, right? With yj. Basically, from the split classes, we determine how impure it is, right? How impure it is. If it is totally the same class in this split, or it has a mix of different classes. So now we just check if the impurity we just found is less, right? If the split is better than what we have found before, and what we have found that it was impurity best, right? It was impurity best. So then, if this impurity we just have found, if this split is actually better than we had before, when we change it, right? So it's then impurity best equals impurity, all right? So we take this actual split as being the best one, and the split best equals to I. This is if feature and j split, right? So we take these two guys. Okay, so after everything, we just basically return split best, right? Split best. Okay, we just return split best. So the question, there are two questions in this algorithm. One algorithm is how do we split one algorithm, and another question is how do we compute the impurity, right? Okay, so basically splits of xi, right? We calculate like that. If xi is the categorical value, right? If it is a categorical value, so basically nominal or ordinal, doesn't matter. So we then split by category, by distinct values, right? By distinct values or categories, right? Or classes, as you want. Classes, right? So if we have a feature that's basically true or false, so we have split on one end these are truths, on other end these are falses, right? So this is a split. If we have countries, so we have a number of splits that basically by the country, right? So Lithuania, Latvia, Estonia, these are examples that I'm giving you, all right? Okay, if xi is the continuous value, right, of continuous type, then we basically, what we do, we take unique values. We take unique values, right? So these basically distinct values. We take all the unique values, right? What we do then, we sort them, right? So we basically take from lower to under to higher, and then we return middle values, right? And calculate middle values, right? So basically, if we had, for instance, if these were true and false, for instance, right? This would be returned, right? So if we had 1, 2, and 3, we would return a half, right? 1.5 and 2.5. These are middle values, right? So for continuous, we just split in between the distinct values, right? In between the distinct values. This is one of the possibilities how we can split. Okay, so this is how we basically split. For each feature, we go and check if it's categorical or continuous, and we split depending on this algorithm. All right, so okay. So now we need to calculate the impurity. All right, so impurity, once we did the split, impurity of the split is, okay, I will write it down. This is impurity of y. Is basically we have multiple options. We can calculate errors. This is the most simple one, right? Errors, which is equal of number of errors with respect to majority class. Majority class divided by the number of observations in this partition, right? So basically, if we had A, and B, right? So the majority class is A because they are more than anything else, right? So this is a majority class, right? This is majority class, and one of them is out of sync, right? So what we have, 1 divided by 1, 2, 3, 4, right? 1/4. This is the error that we have, right? If no errors are there, right? If all A's, if all from the majority class, then we will have 0, right? So we will have 0 errors. Okay. The other possibility is to use the Gini impurity that you already know, right? That you already know, or entropy, right? That you already know as well. We have looked into that. Okay, now since we have, we can calculate these for each of the branch, right? So for each branch, let me go for each split, right? Each split partition, right? Okay, so now to calculate the overall quality of the split, right, we need to calculate the impurity of split. Impurity of split, or y, right, is actually equals to the sum of all splits, sum of all splits, where we have the number of items in the split, right? Number of items in the split divided with respect to the overall items, right, in this partition, times the impurity of yi. So basically, if we divide into two chunks, right, into two, we split data into two things. We calculate impurity for one and calculate impurity for the other, and then we just basically normalize it by the number of items, number of observations that fall into one part and the other. So this is some kind of a normalized split impurity, but it's actually the single number for the split. So this is what we actually calculate here, right? Impurity of the split. Let me put here a small word of split. Split, okay. Okay, so we have impurity and we have the impurity of the overall split. Okay, so now what's left? We have an impurity of the split calculated. Then we have the splits calculated. So this is fine feature. And now we need to look into the stop condition, right? And the last thing what's left. So basically stop condition for the algorithm is such, again, we have options, right? Then the impurity of split, right? Impurity of split equals to 0. So basically we have reached the best possible split. So we basically constructed the decision tree, which have split to the very end. But this can be an overfit, right? Overfit condition, question mark, right? Okay, so now we can calculate something like the impurity of some branch, of some new branch, is actually less, is more or equal to the impurity that was best, right, for us of y. This basically means that if we split some more, we do not gain any better. So we have found a split, which is not that good, right? So basically, maybe this is a condition to stop. Okay, the other condition could be that all features were splitted. Right. So basically we have split on all the features, right? And so we can stop. We just basically don't want to split anymore. Okay, the other condition could be max depth reached, all right? So basically we have reached some depth we have predefined for ourselves as a hyperparameter, all right? What we can have some more. So for instance, minimum samples at leaf reached. So there's no more reason to split because our leaves are small enough, right? So, or some minimum impurity decrease threshold reached, right? And so on. So there could be some more conditions or combined conditions that you just decide to stop splitting. Okay, so now let's take a look into the example so it will become much clearer for you. Okay, I guess it will become clearer because examples are sometimes explaining it better. So, okay, let's have a data set. Again, two features, x1 and x2. And let's have, again, as a class, as a true class, y, axis, and circles. So, okay, so this 1, 1, 1, 2, 2, and 2, right? 1, 2, 3, and 1, 2, 3. Okay, and this is x. This is circle, x, and circle. These are the classes, the binary classification problem, right? So now we basically can put a graph so we display the data correctly. Okay, so this is x1, x2. So now we'll have 1, 2, and 3. Here again, 1, 2, and 3. Okay, so now here 1, 1 we will have an x, right? 2, 1 we will have 2, 1, we will have an x as well. This 3 is not needed for x1, it's just 1 and 2. Okay, 1 and 2, 1 and 2 is a circle. Okay, 2 and 2 is an x. Okay, and these two are circles. Okay, so this is kind of situation, and we will be running the decision tree algorithm in order to find out how to split it, right? So, okay, so let's do it. So step 1, step number 1. Okay, so since these are, let's say, continuous values, right? So these are continuous values. So our first split will be on x1, right? On x1, this is the first feature, right? First feature, and we have in between, right? We have in between the split. So let's make a condition. x1 is less than 1.5, right? This is the condition for splitting, right? x1 is less than 1.5, right? Let's calculate the error. So we are about to have a candidate split right here. All right, okay. So what we have, a impurity for this side, right? Impurity for this side, the majority class, we will use errors, right? We will use errors because they are much simpler to calculate than Gini impurity or entropy, right? So we will use errors here. So this basically, the first part, right? It has 3 observations and majority class is the circle, right? So 1 is error. So 1/3, and this part has the same situation. Majority class is x, right? And the error is 1. So 1/3 as well. 1/3 as well. So basically on this side, from overall observations in this partition, now partition is the whole data set, right? We have 3 and 3. So basically we have 3/6, right? Times 1/3 and plus 3/6 as well on the other side, right? Times 1/3, right? So this is the impurity of the split, right? And once we multiply this, so this becomes 3 and 18, 3 and 18, so 6 and 18, so 1/3. So this is the impurity of the split, of this exact split, right? Okay, so this is a candidate for the split. We just have calculated the impurity, 1/3. So now let's take another example. So we want to evaluate another example. So let's take this guy, all right, as an example. So we are going to the other feature because there are no possibilities to split on x1. Now we will try to split on x2, right? So this split, right? So this would be x2 less than 1.5. Okay, another candidate split. So what we have here is that we have 2 x's on one side and 3 circles and 1 x on the other side. So basically this is 2/6 times 0, 2, right? 0, 2, because there are 2 x's and no errors. So majority class is x, everything is fine, plus 4 6's. On the other side, we have 4 observations, right? And okay, times 1/4, right? Times 1/4, because 1 is an error. Majority class are circles, but 1 of them is an error. So basically, by doing a calculation, this becomes a 0, right? This is 4 and 6, right? So basically, this simplifies to 1/6. Okay, so this is an error. This is an error, impurity, right, for one guy, and this is impurity for the other guy, right? So obviously this one is better. If we look into this split, that would be a candidate, right? We would see that exactly the same situation, right? Exactly the same error, because it would have 2 circles on that side and 3 plus 1 of 3 x's in 1 circle on the other side. So by splitting on 2.5, we would not gain any more information, right? So this is a candidate for split is less than 2.5, right? So error equals 1/6 as well. So basically, obviously, by our algorithm, we are choosing this, right, as the first candidate to split. Okay, so this is the split we take, right? This is the split. So this is the first split. Okay, so for the step 1, so this is best, right? Best. Okay, so step 2, step number 2, quickly. Okay, step number 2. So again, we can split step number 2. X1 is less than 0.5. So let's skip this step because it's already error equals 0, right? For this branch, error equals 0. So we will not split. So what we will evaluate, this partition, right? So because we have split, so we have 2 partitions. One partition is that one of observations, another partition is this one. So this one we can consider as done because it is error equals 0, right? So this partition is what we will be looking at. So the first candidate for split is actually this one, right? This one and this one. As you can obviously see, those 2 splits would make exactly the same error, right? Because it would split into the circles and the 50% error, right? And this would split into the circles and 50% error as well. So basically step 1 would be the best split, x1 less than 1.5. All right, so this would be the best split, obviously, because the other split would gain the same error. So this is 2/4, 2 out of 4 times 0, 2 plus 2/4, just split into the same chunks, right? Times 1, 2, right? So this is 2/8, so 1/4 error, right? If we would try to split x2 less than 2.5, we would just get the same error. Error equals 1/4. So exactly the same situation, so no gain. We take as best this one for the second split. Okay, so obviously once we did first split, the second split for this partition, right? Second split. Okay, this is the second split. So once we did that split, this part does not need any split, do not need any splits anymore because this is actually already pure, already have the same, this single class, and this can be still split, right? Obviously, and this is only one split possible, so this is 2.5, right? 2.5, and this will gain 0, right? So step 4. Step number 3, actually not 4. Okay, so the only split is possible, x2 less than 2.5, right? And this will gain us an error, which is equal to 1 out of 2 times 0, 0 of 1, right? Plus 1 out of 2 times 0 of 1 equals to 0. So basically, we've got to the best situation possible. Okay, so basically this, after all, have constructed us a tree which can be expressed like that. Okay, so basically we have constructed a decision tree where we have the first split. So, okay, x2 less than 1.5, right? This is a first split. And the situation before the split, right? The error before the split, or the probability of deciding where do we need to go, is actually 50-50, right? Because we have the majority class is, for instance, circles, right? Majority class would be circles. It doesn't depend us for which one to choose. And since we have the same amount of observations for the class, right? We have free and free. So the choice of which class is to be chosen is the same. So we can tell that before the situation, actually it is circles. We just choose circles as a majority class, and the error is 0.5. Error is 0.5. So this is initial situation. But after the split, after we've chosen this split, right? So this is true, right? This is true. This is false condition, right? x2 less than 1.5, right? So basically this split, x2 is less than 1.5, right? So if it is true, if x2 is less than 1.5, right? So now we've got into the situation where we have x's and the error equals 0. So we basically, after this decision, and if it is true, we've gone to this branch where everything is just x's. No options for circles remain here. Now here we are in slightly different situation where we have an error. If we remain here, we will tell that we are at circles, right? We are at circles because circles are the majority thing, right? After the split, circles are a majority class, right? And the error is 1/4, right? 1/4. So the probability to actually make it correct is 0.75, right? The accuracy. We could tell the algorithm that accuracy would be 0.75. Okay, so, but we do not stop here. We just split again. x1 less than 1.5, right? x1 less than 1.5. We split here, this branch, upper branch. Okay. And what we land up at, okay, so again, this is a true condition and false branch, true and false. So we have here, if it is false, right, if it is false, so we have only circles remain, right, only circles remain. So this is circles and error equals to 0. If it is false, right, if it is false, so again, we are undecided if it is circles or x's. So we just don't know because it's 50%, right? So we can tell that we are the different class when it was here. So we basically choose, okay? So we basically choose that this is x and e equals to 0.5, right? So you see we had error here as being 1 divided by 4, 0.25, and now we have an error increased actually. Once we've gone here, our error has increased. So our probability of deciding now is not that certain, all right? Okay, but we do not stop here, and for us, we just split again. Less than 2.5, right? And again, we have a situation of being true and false. Okay, true and false. So, okay. And I can tell you that if it's true, then these are x's and error equals to 0. And if it is false, if it is more than 2.5 by x2 feature, then these are circles and error equals to 0. Okay, so basically this is how we have constructed our decision tree, and the actual boundary would go somewhere like here, right? Between the classes, here, here, and right here. So this is a boundary between our classes, and it is actually well defined by using this decision tree. So this is how decision tree actually is being constructed, right? By making a condition, by finding the best split at the moment, by looking into the feature and split impurity. So once you find it, you do the split, and then you work with these partitions only. So basically you split the split and data set into many different parts. Okay, so basically now we've got a situation that we could stop after this, right? After this, after this, not going into that. So the condition stopping here would be all features split, right? All features split, because we would split by x2, we would split by x1, and that's it. We remain here, right? All features split condition for stopping. The other possible stopping condition that the error current is less than error split, right? We have found a split which actually has the larger error than the current, right? So it is not good to split anymore because we just increase error. If we go into this branch, we just more uncertain, right? Okay. Or for instance, going this down, right? This down, the whole tree. So basically, this is an error split until error equals 0, right? Error until equals 0. So we're going down to the very end. So as I've mentioned already, this is an overfit condition, possibly. Overfit condition. Okay, I guess that was it for today. So I explained you a couple of techniques. One of the technique is basically how to derive and how to construct logistic regression algorithm, the gradient descent and the algorithm itself. This is one way how to do it. The other way, for your convenience, you can take it or not, is basically construct the decision tree algorithm, which can work like this. You have options how to compute the impurity. The simplest one, error. The other options are Gini impurity or entropy. You choose, and then you basically calculate the split cost, right? The cost for the split. Stop condition you choose, whatever you want, right? But keep in mind that if you would split, for instance, to the very end, you would most likely overfit, right? So basically, splitting data sets into the training, validation, and test sets is required anyways, regardless if you're using the decision tree or logistic regression algorithms. And choice of features, choice of hyperparameters are all needed for the classification as well. Okay, so next week we're gonna have the break. We have the holidays, So after the holidays, we will still have one lecture for reclassification, where I will talk you about the metrics, about the evaluation of the classification results. Victoria, you're asking that this goes only for binary problem. You mean the decision tree, I guess? No, you can do it for multiple class problems as well. You just basically find the best one, but you need to, yeah, so I don't know where are the changes. Well, and anyway, you will be looking into the majority class anyway. So basically, decision tree can be adapted to multiple classification problems as well. Because after split, you have a majority class, you look up what number of errors remain, and just continue. For the impurity, for the Gini calculation and entropy, you can do this as well. But these algorithms were presented a bit earlier. Okay, so any more questions about this? Okay, so basically, I think you will have video. You can go it over again if you liked it. If not, then most probably you memorized it already. So yeah, so meet you after the meet you tomorrow. Actually, most of you will meet you tomorrow, and we'll talk Java a little bit. Okay. Bye bye then.